A point z0 in C is a limit point of S, which is a subset of C, if and only if the following condition holds. For every epsilon greater than 0, there exists a z in this set S, such that z is not equal to z0, and the modulus of z minus z0 is less than epsilon. The first part says, write down the statement equivalent to z0 is not a limit point of S. Now, looking at a question like this can be quite daunting if you're not experienced in this sort of notation or these concepts. But for us as a HSC student, we really only want to think of this as some logic statement that needs to be dealt with in a certain way. So we've been given this statement, which is the definition of something being a limit point. We want to write down what it means to not be a limit point. So in other words, we want to write down the negation of that statement. So for part I, all I'm trying to do is write down the negation of the given statement. Now, the statement that we've been given is a quantified statement because we have these quantifiers out the front. And so we need to take the negation of a quantified statement. And so how do we do that? Well, we negate the quantifiers, keeping them in the same order, which basically means whenever we have a for all, we swap it to a there exists, and vice versa. Whenever we have a there exists, we swap it to a for all. So we start off with there exists an epsilon greater than 0 for all z in S. And now we have to negate the actual statement itself. And if you see what we have within this statement, we have an A and a B. Okay, or if we are really using logic, probably we should draw it more triangular. A and B. Now we want to negate that. And to negate A and B, to negate this thing, we're going to have to use De Morgan's laws. So what happens is the negation gets distributed throughout the brackets, the negation of A, negation of B, and then the and becomes an or. Okay, so I'm just going to move this down here, get it out of the way. Now I can finish off this negation. So for there exists an epsilon greater than 0 for all z in S, such that z is equal to z0 because I have to negate this, or now I have to negate this one here, z minus z0 is greater than or equal to epsilon. Okay, and that's it. There's 2 marks there. I think that's pretty manageable for us as Extension 2 students. We didn't really have to understand what the statement was saying. All we had to do was know how to take the negation of a quantified statement. Okay? Now, let's have a look at the next part. It says, let S be the set of Gaussian integers, where S is A plus IB, such that A and B are Z. Now, what this is saying is that S is a set of all these complex numbers where A and B are integers. In other words, the real part and the imaginary part of the complex numbers can only be integers. Then it says, explain why no limit points of S exist. And they give us a hint, which is to consider a couple of cases. The first case is when Z0, the limit point, is in S, and when Z0 is not in S. Okay, now I think the first problem with this kind of a question is to try to understand what the Gaussian integers are and what they look like. So what I'm going to try to do is I'm going to try to draw this up to give us a visualization of what these points look like, because this is a set is a collection of points. I want us to make sure that we understand what that looks like, and I think that's going to be really useful going ahead with this question. If we're trying to prove that there's no limit point, seeing what it looks like will be really useful. So I'm going to quickly draw that up, and this is what we get. We get all of these green points here being elements of the Gaussian integers, and I think that makes sense because it's all of the points whose real and imaginary part are whole numbers. Okay, so basically if you mark off 1, 2, 3, 4, 1, 2, 3, 4, etc., it's all of these grid points, or sometimes we call them lattice points in the plane. So all the points in between these, everything in here, in here, in here, in here, all of those points, they're all just regular complex numbers. This is a subset of the complex plane where we've only taken the grid points or the lattice points, and those are what we call the Gaussian integers. Okay, and they're actually quite important and useful in high-level maths, okay? But we don't really need to know too much about that just to do this question. So what are we trying to do? We're trying to show that if we have some point z0, which is a complex number, let me go back up to the question. We're trying to show that if we have a point z0, which is any complex number, it need not be in the subset S, but if it's any complex number, then it's never going to be a limit point of this set of Gaussian integers, okay? And it even gives us a hint here. It says to consider when z0 is an element of the Gaussian integers and when it's not an element of the Gaussian integers. Okay? All right, so I'm actually going to start with this second one here. I'm going to start with the case when z0 is not in S, and then I'll come back to this one here when z0 is in S. So the first case that I'm going to work with, case 1, is to suppose z0 is not in S. So what we're trying to do is we're trying to show it's not a limit point, which means we're trying to show this condition is true. Now, we need to try to understand what this condition is saying. So let's go through it. It's saying that there exists an epsilon greater than 0 for all values of z in S. So I'm trying to find an epsilon which is positive, such that for all of these green points here, either the z is not equal to z0, or the modulus of z minus z0 is greater than or equal to epsilon. Now, the very first thing that I can notice in this case is that obviously this is not true, because our z0, as we said, our z0 is not in S, and we're talking about z being in S. Okay, so my z0, if I was to place it somewhere, maybe it would sit, like here, not on one of those lattice points. This is my z0. I'm just going to label it over there, z0. Obviously, z is not equal to z0 because it's not a lattice point. So I can say here, obviously, z is not equal, or maybe I should say the other way around, z0 is not equal to z for all values of z in S, okay? Since z0 is not in S. So that means I can't prove that it's not a limit point by showing that. I must have to show this. Okay, so let's try to understand what this is. This is saying that the modulus of z minus z0 is greater than or equal to epsilon. Now, if you think what this looks like, to me it looks like a locus problem. It's one of those standard locus forms where you've got a circle at some center with a given radius. And this one's going to end up being a region because it's not equals to, it's greater than or equal to. Okay? So this here is basically saying that we have a circle whose center is at z0, and it has a radius of epsilon, and we want all of the points outside of that circle, either on the circle or outside of the circle. So it's that region. Okay, so let's now try to understand exactly what we're trying to show. I'm trying to show that I can find a value of epsilon, because I only have to show that there's one of them. That's what there exist means. I have to show that there is at least one value of epsilon, such that for all values of z in S, that means for all of these green points that I've got, I can draw a circle so that all of those green points are outside of my circle. So is that possible? Is it possible for me to find such a radius, such a value of epsilon? Because remember, epsilon is representing the radius of my circle. Is it possible to find one? Well, of course it is. It's very easy to do it. There you go. If I draw a nice circle here, I'll try to draw it properly. There's a circle with a center at z0, and all of the green points are outside of that circle. So intuitively now we've understood that it's possible to do this, which means that in this case, where Z0 is not an element of S, then there is no limit point. Okay, now what we have to do is we have to turn this intuitive understanding into a coherent and logical argument. So basically what this boils down to is me making sure that my radius of my circle is small enough so that I never capture one of these green points within my circle. So how could I do that? Well, this is how I would set up my argument. I would say something like, let W, which is an element of S, be the closest point to this supposed limit point, Z0. So let W be the closest point to Z0. And the reason I choose the closest point is because as long as I can make sure the closest point isn't within the circle, then all of the others can not possibly be in the circle. So I'm letting W be the closest point. And so therefore, what I have is this length, Z0, W minus Z0, that length there is as small as possible for all elements of S. Okay, for all my Gaussian integers, I can never get a distance smaller than this distance here. Okay, so I've got this distance, and what I want to do is I want to make sure that my radius is small enough to never capture the closest point. So in this scenario, here I would have to make it so that my circle doesn't do something like this, where it's captured the closest point right here, okay? So what would I need to do? Well, I need to find a radius which is smaller than that distance. Okay, now I don't know what this distance is, so I don't want to subtract off something because I might subtract off something and then end up with a negative radius. That's dangerous. So how else could I make my radius smaller? Well, I could divide it by a number. I could divide it by 2, I could divide it by 10 if I like. Doesn't really matter, but dividing by 2 seems like, I don't know, the most obvious thing to do. We want to just halve the radius, or half that length to give us a radius. So we will choose epsilon to, let's draw that a little bit neater, epsilon to be equal to 1/2 of this length here, W minus Z0. And by doing that, we're now ensuring that W won't be included in the circle. And if W is not in the circle, it's the closest point. That means no other Gaussian integer could be within the circle. Okay, and so therefore we have, for all of our values Z in S, we have to have that the length of Z from Z0, that would have to be larger than or equal to 1/2 of this length, W minus Z0. But this is what we chose to be our epsilon. And so I can make like a final line, Z minus Z0 is greater than or equal to epsilon. So what I've done is I've showed that there exists a value of epsilon, so that for all of these values of Z, this is true. And so therefore Z0 is not a limit point. We can write that concluding statement. Therefore Z0 is not a limit point. And that's the end of our first case. Okay, now for our second case. The second case, it even tells us in the question, is to consider when Z0 is an element of the Gaussian integers. So I'm going to go down and write case 2. Z0 is in S. Okay, so once again, we're trying to prove that we don't have a limit point if Z0 is in S. But it's good to be able to visualize this. Let's take, maybe this time I'll use orange, and let's say that this is where Z0 is. So Z0 is one of these lattice points. And what we need to show is, once again, this statement here, that there exists a value of epsilon such that for all of these Gaussian integers, either z is equal to z0 or z minus z0 modulus is greater than or equal to epsilon. Okay, so what we're trying to do is we're trying to find, remember this is representing a circle, we're trying to find a radius, a value of a radius, so that if you're a Gaussian integer, you are either equal to z0 or you're outside of that circle, on the boundary or outside of that circle. Okay, so let me give you an example of a radius which would not be beneficial. So if I had drawn my circle in this way, hopefully that comes out somewhat neat. If I draw my circle like that, okay, let's think about what we've got here. We've got 1, 2, 3, 4, 5, 6, 7, 8, and 9. We've got 9 Gaussian integers within my circle. And why this is not good is because we're trying to show that if you're within the circle, we're trying to show that if you're a Gaussian integer, you are either z0 or you're outside of the circle. Now for these 8 on the sort of border, if you like, these 8 ones that I've just marked in red there, they're not outside of the circle and they're not equal to z0. So this value of epsilon, this radius, isn't a useful value to help me prove what I want to prove. Okay, I want to basically show that I can find a circle, a radius of a circle. I want to be able to find a radius so that the circle only contains z0 and all of the green points, all of the Gaussian integers are outside of that circle. Can I do that? Yep, I can. I just reduce the size of my radius. Like this, there's a possible circle. Okay, and the circle obviously is determined by the radius size. So the question is, what value of epsilon do I need to choose? Because that's what it comes down to. It comes down to, can we choose the correct value of epsilon? That's what we did over here. We chose the correct value of epsilon as being half of that modulus of w minus z0. What would the correct value, or what would a correct value of epsilon be in this case? Well, once again, we think about what the closest point to our z0 would be, closest Gaussian integer. It would be one of these 4 here, and they're all 1 unit away. So as long as I choose my epsilon small enough to miss these ones, then I'm definitely going to miss all of the others, because those 4 were the closest. So if it's 1 unit away, I just choose my epsilon to be less than 1. Okay, so here we go. I'll probably say here, just writing it so you know what I'm doing. We want to choose epsilon greater than 0 such that, that's an abbreviation for such that for all z in S, either z equals z0 or z minus z0 is greater than or equal to epsilon. Okay, so another way of saying that is that if we choose a circle, it only has the one Gaussian integer within it, which is z0. Otherwise, all other Gaussian integers are outside of our circle. Okay, and I will show you how we can reformulate this thing to make it a little bit more intuitive to see. Okay, but anyway, we've said that we just choose epsilon to be anything less than 1. So we've chosen epsilon to be anything less than 1. The closest points, or the closest, let's say, the closest Gaussian integers to z0 are 1 unit away. Okay, they're 1 unit away, and so therefore, for all of these Gaussian integers, if epsilon is less than 1, either z equals z0 or z minus z0 is greater than or equal to epsilon. Okay? And really the crux of this, the justification is that the closest Gaussian integers to z0 are 1 unit away. That's basically justifying our claim here. All right? And so therefore, z0 is not a limit point. And we've proven both cases. The case where z0 is in S, the case when z0 is not in S, and so therefore there is no limit point. Now, I did say that there is an alternative way of expressing this, this statement here. So what I'm just going to do, I'm going to copy this down because I want to I want to make sure that you understand this equivalence as well. All right, so we can actually write this or statement can be written as an implication, and it becomes a little bit more intuitive to see what we were discussing if it's written as an implication. So let's quickly just discuss implications. If I say something like P implies Q, what this means is that if I have P, I definitely have Q as well. Whenever P is given to me, Q comes along for the ride. I don't get a choice, all right? So if P always gives me Q, another way of saying this, an equivalent way of saying this, is that I can never have P and not have Q. Okay? P always gives me Q is the same thing as saying I can never have P and not have Q. So that last sentence that I said, or that last little phrase, let's turn that into some logic. I can never have, it's not possible for me to have P and not have Q. So these two statements are logically equivalent. But then this statement, I can write something logically equivalent to that by using De Morgan's laws, right? I distribute the negative through to both of those, and then I flip this and into an or. And so this is logically equivalent to saying not P or not Q, which just brings me back to Q. Okay, so if I have P implies Q, here are two other statements which are logically equivalent to the implication P implies Q. Okay, so this is a really useful thing to know, especially if you have to take the negation of an implication. The negation of an implication is negating this or negating this. Okay, so that's quite important to know. But now in the context of what we're doing, I want to rewrite this here, which has an or statement. I would like to rewrite that as an implication. And the way I'm going to do that is I'm going to call this statement here not P, and I'm going to call this one here Q. All right. So to rewrite this as an implication, it's now going to be there exists an epsilon greater than 0 for all z in S. Now I have to have P implies Q. So I need to have the negation of this implying this. Well, what's the negation of that? That's just going to be z minus z0 is less than epsilon, implies that z equals z0. Okay? And now it's a little bit easier to see what we were trying to explain before. So I'm trying to find a radius so that for any value of S, if it is between, or if it's within the circle centered at z0, then it has to be z equal to z0. It has to be that center. Okay? It has to be the supposed limit point. That's what we're trying to show. And I think that's very obvious. If we go back up here, here's my circle. If there's a Gaussian integer within that circle, it has to be z0. And there it is. Okay, it's the orange point z0. I probably should have labeled that as such, z0 there. Okay, so it's much easier to see it if it's written in this form. And that's actually probably the way, if you were doing, some analysis course at university, that's probably the way that you would see this written. It's more likely you'd see it written as an implication than as an and or an or statement. All right. But anyway, that is the end of the video. Hopefully it gave you a little bit of insight into how to deal with something like this. Personally, I don't expect something like this to pop up in a HSC, but weird things have happened in the past. Okay.